Moving beyond small rovers to drop city-building payloads onto the Martian surface requires a complete shift in how we think about getting there. Right now, the peak of chemical engineering is SpaceX's Starship. It is the most powerful rocket ever built, but even its massive scale is constrained by the physics of liquid fuel. To send a single fully loaded Starship to Mars, we have to launch 10 more of those massive boosters just to truck up enough fuel to refill the primary vehicle in Earth's orbit. To break this bottleneck, NASA is building Space Reactor 1. Scheduled for the 2028 transit window, it is designed to be the first interplanetary nuclear-powered spaceship. Establishing a permanent presence on Mars means abandoning the pursuit of explosive speed. To move the heavy gear required for colonization, NASA is prioritizing extreme fuel efficiency over a fast arrival. The most direct path for nuclear flight is a nuclear thermal engine. It works by pumping liquid hydrogen through a fission reactor, where the heat flash boils the propellant and blasts it out of a nozzle for thrust. This method is 5 times more efficient than chemical combustion and could theoretically cut the transit time to Mars down to just 45 days. NASA rejected this option because it still relies on carrying massive, heavy storage tanks for liquid fuel. On the ship of this scale, that fuel weight directly displaces the cargo we actually need to send. Deep space logistics is a problem of mass, not just velocity. Moving heavy infrastructure requires an engine that moves away from liquid propellants entirely. Instead of thermal thrust, NASA chose nuclear electric propulsion for the SR1. While standard Earth-based reactors generate about a gigawatt of power, the SR1 uses a modest 20-kilowatt commercial-scale reactor, roughly the output of a home backup generator. The system vaporizes liquid in a closed pipe. The expanding gas spins a turbine connected to a generator, creating a power cycle. This electricity feeds an ion thruster, using magnetic fields to fling electrified atoms out the back, creating steady thrust without combustion. Because the system pushes slowly but continuously, the SR1 will take an entire year to reach Mars. Sacrificing short-term acceleration makes the ion engine 10 times more fuel efficient than a chemical rocket. This turns the SR1 into a heavy-lifting freight train for the solar system. Taking a full year to reach the red planet is only justified if the payload itself is critical to our survival. That payload is Skyfall. Upon arrival, the SR1 drops an entry capsule that deploys 3 autonomous helicopter drones directly into the Martian atmosphere. These drones use ground-penetrating radar to scan vast areas, like this 2-kilometer rocky stretch, hunting for the subterranean water ice deposits needed for drinking water and return fuel. Equipped with high-resolution cameras, these scouts are searching for the flat landing zones and foundational resources that determine whether a human colony succeeds or fails. NASA views the SR1 Mars mission as the inaugural run of humanity's nuclear railroad. The immediate follow-up in 2030 is Lunar Reactor 1, a power station designed to keep human systems running through the freezing 14-day lunar night when solar power is impossible. The shift to nuclear electric systems replaces temporary flags and footprints missions with the heavy-duty planetary infrastructure required for a permanent human presence in the solar system.